Okay, go.
Hi, my name's Ryan.
My name's Tyler.
And I'm Myron.
I'm Diego.
And I'm Jake.
And this is our Opti 380A final project.
The purpose of this project was to make a rangefinder using nanosecond pulse time-of-flight LIDAR. This was done by using a beam splitter and measuring the time into a single detector between the original pulse and the pulse reflected off a target object. The motivation of this experiment is to use the high spatial resolution given by the nanosecond pulse to determine the distance with a high degree of precision, as well as examining how the relevant components affect signal accuracy and fidelity. Important topics that are covered in this are beam splitting and recombination, beam interference, and pulse duration. This is significant because of the many detection systems that LIDAR is used in that need high precision and quick operation.
To give a little background on light detection and ranging, also known as LIDAR, the main principle is that you have a laser that shoots light onto an object, reflects off the object back into a detector, which you then measure the time of flight by taking the pulse of the laser and the detector signal and measuring that change in time. You then can calculate the distance by doing the speed of light times the time of flight divided by 2. LIDAR is used in many applications such as rangefinders or self-driving cars to image the environment around them.
So next, here's our optical setup, where we're using a 905 IR laser followed by a 55mm focal length lens to collimate the light into the beam splitter, where the light is then split and it hits the mirror, and the light reflects back into the beam splitter where the light is recollected and is sent into the APD, which is a 400 to 1000 nanometer wavelength photodetector, which in front has 2 ND filters to prevent oversaturation and a pinhole to filter out external light.
Okay, so for the system alignment, we want to keep everything at a consistent 5 inches to the center of all the components. And for this meant raising the APD and the laser and the associated components with that. But it also meant 3D printing custom mounts for the beam splitter and 2 servos, which will be talked about more later. And right now we currently have one of these servos pointing directly back at the beam splitter to act as the object.
To get measurements, we wrote a MATLAB script that takes the waveforms from the oscilloscope, measures the time of flight, averages 100 measurements to get the distance from the laser to the object. So as you can see, it connected to the oscilloscope, and we should get measurements soon. And this is in meters. And now as we move the object further back from the laser, you can see that the distance will increase in our measurements.
We did the experiment with an object at 4 different distances, as you can see here on the left, and then these were the averages across 500 separate trial runs here on the right, done with automated MATLAB code. The percent error for each of these runs is in the next column over. As you can see, the percent error is very low for each run, however, they are very inconsistent, and there's no specific amount of error that it keeps being off by. This is likely because the main source of error was us slightly incorrectly calibrating the oscilloscope, as that was a very difficult step that took a large amount of time to do. The data has also been plotted here in this graph. The blue line is the expected line, where the actual distance should be the measured distance, and then the orange line is the trend line for each of these data points.
Overall, the objectives were greatly achieved and the project was done before the due date with no major problem. However, our LIDAR system contains some limitations, such as the noise from the detector and oscilloscope, which makes our output signal unstable and incorporates some errors in our measurement. We were also limited for the maximum distance we could resolve in our system since our ND filter was very strong. To measure long distance, the filter would need to be changed, otherwise the noise would become greater than the output signal, making the data unreadable. For future work, we can incorporate 2 mirrors attached to 2 automated servo motors to create a LIDAR point cloud for mapping objects.